So we talk about related rates. And when you think of related rates, you have to have some sort of imagination. It's not that much of an imagination. What you always imagine doing is what you do most of the time. You watch YouTube video. So imagine you watch a YouTube video of a very simplistic model of an oil tanker that's leaking. Okay, so what happens is that you can see the time bar as it goes out. The leak is expanding, and it's always expanding at a calm sea in a perfectly circular pattern. Okay, so you see a smaller circle, then a bigger circle, and so on, right? Nothing else is happening. The water is not moving. The tanker is stationary. It's a very simplistic, bare bones model of a tank leaking oil. Now, the first question is, what data changes with time? Would you go ahead and try to list data that changes with time?
Possibly, you would probably think, I'm using my phone, by the way, also.
That's fine.
Wouldn't like the radius and like the circumference?
Exactly. And Alexa said a similar thing. She said circumference will change with time, the radius will change with time, and since in this case it's like two-dimensional spill, so the disk will change in area as a function of time. Yes?
Yeah, the parameter.
Yeah, so those are some of the parameters, and as Batel says, radius and c will change as a function of time. And what it means is that even though you do not see an exact formula for how r is to be determined by t, or how c is to be determined by t, or how the area of the disk is determined by t, right? If all of those,
if you put them all into formulated forms, into formulas, then they all carry context clues that relate to each other in a way.
Exactly, that's the point, right? So again, when Alexa says it would be interesting in the real world, the thing is this model is so far remote from a real tanker leak that it's meaningless. All right, guys, if you have noise in background, would you mute yourself, please? Thank you. So here is what we mentioned, right? So A is a function of time. It's A of t. D, the diameter, is a function of t. The circumference is a function of t. And by that, what do I mean? I do not see the explicit formula if I'm watching the video, but as I'm moving the time, a definite moment of time corresponds to a definite radius, a definite circumference, a definite area, a definite diameter. So that means that since it's not ambiguous, there is a definite quantity for each moment of time. I can think of those quantities as controlled by time. Okay. So,
Professor,
yes,
so the area is the big circle, right?
The area is, well, the big circle or the small circle, it's just they are changed with time, right? So, yes. So at this shaded time t, that is the area. At a later time, the disk is bigger and there would be a bigger area, right? So those are rates, because rates are just quantities that change with time. And those rates, as I just heard Joel mentioned, those rates are related to one another. So for example, the area at any time t is pi times the square of the radius, right? That's because they are circles. So the circle always has this property that it's pi times r squared. And the circumference is 2 pi times the radius. And the circumference is pi times the diameter. And
by related, like when I said related, I meant that when you have a radius and circumference, you can find all the other things that you need by using those measurements.
Yes, you can. If you know the circumference, you know the quantity for all other properties. That's precisely right. Right. So so here I could relate the area to the circumference, because circumference is 2 pi times r. So if I take the circumference and divide by 2 pi, I get the radius. And if I square it and multiply by pi, I get the area. So I can see that the area is 1 divided by 4 pi times the circumference squared. Yes?
Yeah.
Yeah, so this is just why the topic is called related rates. You are measuring how one quantity changing in time affects another quantity also changing in time, and you are comparing their velocities that are dependent on one another. So here is that same example, but let's try to solve a few things about it. So suppose that the tanker is leaking oil at a constant rate of 2 meters squared per minute, which means that the area somehow, because you know how fast is the faucet spilling, how fast is the oil emptying into its two-dimensional lake. We know that it's 2 meters squared per minute, okay? So several questions to see how you feel about this quantity. You have to imagine it. So first question is the rate of growth of radius increasing, decreasing, or does it remain the same? So first of all, the radius, as area is growing, I spill more and more, you all can imagine that the radius is becoming longer. But the question is it becoming longer faster, or it's becoming longer slower, or it's becoming longer at the same speed? In other words, imagine that you're, what's the new superheroes? Jason Statham, I'm not sure who is now popular. So he is running away from this radius of expanding oil. Well, how fast must he be running to keep his distance to the outer ring fixed? So
I'm not fully understanding, Professor.
The question?
Yeah.
The question is, first of all, the radius, right? You're watching this movie.
Yeah.
You see that this puddle is growing, correct? The oil is being spilled. You know that the oil is being spilled at a rate of 2 square meters per minute. Yes?
Yeah.
Now my question is, how fast is the radius increasing qualitatively? Is the radius, the speed, right? Is the speed of the radius as the puddle grows, is the speed of the radius increases, remains the same, or slows down? You understand?
I hear.
Good.
I would say that the speed of growth of the radius slows down as the area of the oil spill increases, because when you're adding at a constant rate 2 meters squared, then, and it's like expanding outward into the radius, then like at first that will have a big effect on the overall area of the oil spill, but then when you're adding 2 meters, it kind of like spreads out over the circle, and therefore the radius of the circle is growing more slowly than it was at the beginning.
Thank you. So the rest of you guys, do you agree with Alexa's interpretation, or you think?
Well, if what Alexa is saying is correct, then that means that you're taking velocity into account, then you're going to be multiplying velocity times, and if it's constant, velocity times time is going to be equal to the velocity. So that's what I'm getting from what she just said.
Well, so the question is qualitative, right? Velocity, time, all complicated questions, right? So you're running away from the oil spill, right? Or running away from an explosion. The oil spill is much slower. You can run away from it, right? So do you have to be running faster and faster and faster, or as you run longer, you get tired? Can you slow down a little bit? That's the question. Or do you have to keep the same pace?
Got it.
Yes, so Ali Kliji says he agrees it will begin to slow down. And so any other inputs, guys? Do you have a feeling for it? So since I want to move on, I would agree with Alexa as well. Yes, so why does it happen? You can imagine that what happens in essence is that the area, to grow constantly, notice it grows in 2 dimensions, okay? So you can even imagine, right? Imagine that if just the area was a square tile, with a certain amount of time, it would be double the tile, right? To double, notice you don't need to increase the radius that much, right? To double, you see, if you increase the radius twice, for example, if you wait for some time and the radius grew twice, the area has grown 4 times as much. I hope you understand what I'm saying. Okay, I wrote some sort of mathematical symbols there, but essentially the bigger is the space in which we're expanding. So if it's in a three-dimensional space, the radius will be slowing down even faster. Okay, so the radius will be slowing down even faster if it's a three-dimensional space, even faster if it's a four-dimensional space, and whatnot, because the expansion is happening in many directions. Okay, the stain expands in many directions. So if the radius, the time it takes the radius to double will be the time it takes the area to be multiplied by a factor of 4. Do you see that? Because double the radius here, double the radius here, I now have, instead of 1 square, I have 4 squares.
Okay.
Wonderful. So that was the first part. Then the question is for B. The video starts at the moment where the accident just happened. I want you, given that information, to tell me the explicit formula for what is A of t and what is R of t.
Can you go back up for the formula up there?
Well, we don't need it. We know the formula. We know how area of a circle relates to the radius. Yes. So we don't. We want to kind of have the formulas in our hearts as much as we can. So you understand what I asked you to do, guys, right? We know that the area of the spill, which is always circular in shape, the area is basically added 2 meters squared are added every 1 minute. I want you to tell me an explicit formula for A of t, given that you began watching when the spill was a point, was 0.
So if it's, you said 2 meters.
Yes, 2 meters so every minute, constantly the area of the spill is growing. I want you to tell me a formula in terms of t of what's A of t.
Don't you just multiply the t by 2?
Yes, that's brilliant, right? So what you do is you take t times 2, right? A constant rate. So 2, then 2 times 2, then 2 times 3, whatnot. So in general, A of t is equal to 2 times t, right? A of t is 2 times t. And what is then the formula for the radius? What's R of t? Given that I know that A of t equals to 2 times t, what is the explicit formula for R of t?
Divided by pi.
Well, more than that, right? So because you remember what's the relationship? It's R times pi, and the R has to be squared, right?
Why does it have to be squared?
Because area is R squared times pi.
I got it. You're right. My bad.
The square, by the way, it's a Markov dimension. If it's three-dimensional, it would be R2. Four-dimensional, it would be R to the 4th. So the power here actually is a Markov dimension.
I got it. I understand. Awesome.
So for example, circumference would be R to the power of 1 because circumference is a one-dimensional relationship to the radius.
Okay.
Okay, cool. So let me know, guys. I hope you're ready. We can reveal the formula.
Okay. Can I try to answer C? Not now. I mean, give me a second. Actually, whoever wants to can do it.
Right. So write the formula. I'm waiting, guys, and then we will scroll down to it.
Professor, can you repeat what we are looking for right now?
Yes, we figured out what is A of t, the area as a function of time. We want to know what is then R as a function of time, right? So at different moments of time, I have a different size for the circle. You can see for time closer to 0, the circle is smaller. For time later, the circle is bigger. So I want to know what is R as a function of t. How long is it for every t?
Do you want to find a? Do you need the derivative?
Well, Sam already mentioned it. So he is headed in terms of x, but no need to derivative. Just a simple formula. Here it is, right? So R of t is the root of A of t divided by pi because it was squared and multiplied by pi. So it's the root of 2 times t. Sam wrote the equation with x, but it's 2 times t divided by pi. Okay, it would be, so you can see that radius is changing as the root of the area. which is the formula is 2t over pi and square root of it. That's from a equal to pi r squared. Okay. So the next question is, would you tell me how fast is the radius growing 6 minutes into the video? In other words, if I move the cursor to 6 minutes and then press play, how fast, what's the speedometer of the radius growth? What is it gonna register?
I don't know.
Is it 1 over 2 square root of 6?
That would only be the measurement, the length of radius. But what is the speed of growth at that time?
Yeah. So you're gonna take the square root because we need that.
Right. So if you have to imagine something, imagine that this wave of oil is pushing maybe a car or a ship. It's pushing it. And how fast is it going to push, let's say, a car? So the car will show you a velocity, right? It will show you the measurement of velocity. How fast is it moving that car?
Within 6 minutes.
At 6 minutes, because we agreed that it's not a constant rate. First, it's moving it faster, then later, right? The radius is slowing down, so the car will move slower.
No, I was answering this question last time. This is what I was asking for when you pulled the derivative for time. No. See, I'm trying to make sense of this, but I just don't understand it so well.
We will solve it in a moment. But again, guys, that's what I mean. You have to just simply imagine what's happening, right? So when somebody asks me what's instantaneous rate of change, I just think I must read the speedometer. Okay. So t is not r squared. Be careful. So I want to read the speedometer first of all, right?
Oh, okay. So then, so we said before. So will it be 12?
It would not be a nice number, but 12
Okay.
is
Because I'm thinking
there.
12 is the area.
12 is the area. Yes, but the area is not speed.
I hear. Yeah, I don't know what to do.
Would you have to take the derivative?
Yes, of course. That's what derivatives are at the very first. What they mean. So here is explicitly we calculated what is r of t. Correct? We calculated r of t is root of 2 times t divided by pi. That's explicit a formula for r, right? So it's changing it in t. So the derivative, its very first meaning we learned is instantaneous rate of change or instantaneous velocity, which means if I have a moving object and I take a photograph of it, I imagine taking a photograph of the speedometer as well. And instantaneous velocity is the number to which the speedometer points. So r prime of t is the derivative of, this is just a number, root 2 over pi, times root t, which will be root 2 over pi, and the derivative of root t is 1 divided by 2 root t. And if I plug in 6 here, I get 2 over pi root. I have 1 over 2 root 6. So the answer is, well, I can simplify it a little if I want. There is no particular point to it. This is the exact change. This is the exact velocity at 6 meters. Yes, I will post this on YouTube, right? If it records, of course. You never know what happens. So good that you joined, Abdul. So, guys, do you understand?
Not really.
Not really. Where have I lost you, right? So an object, any object, be it a car or anything else that moves, supposedly has a speed. So for any moment of time, supposedly you can imagine it has a speedometer that shows how fast this object is moving. So if you're accelerating, the speedometer will move the arrow to higher speed. And if you're decelerating, it will move the arrow to lower speed. But if I take a photograph of a moving object, I can imagine also taking the photograph at the same time of the speedometer. So if I do not see the speedometer, derivatives as a tool in physics are a way to recover that information, what the speedometer was pointing at. Yes? So if I have a function.
Like a speed trap.
Like a speed trap, precisely. Like a speed trap, so you need to know exactly how fast something was moving. So, what I have here is that we already solved, right? We know that explicitly the function a of t was 2 times t, and therefore r of t was root of 2t divided by pi. You agree? So I have the position function. The derivative of position is velocity, guys.
That I know.
Yeah, so that's all it is. So when I ask what's the speed with which r is growing, I'm asking for the velocity of r. How fast is it pushing some object? So imagine like
at 6 minutes.
At 6 minutes in the video, precisely.
Okay, I understand now. That's it.
So then I take r prime at a general t. That would be this number, right? At a general t, it's given by this formula, and then I just plug in 6, and I get the actual velocity 6 minutes into the video.
So it's just 1 over 2 square root of 6?
Yes.
No, that's, yeah, square root of 6, okay.
Right, so the formula, what it means doesn't matter. What matters, what the number is, we don't care about this question. What the number is does not matter that much. What matters is that you understand that the derivative of position is velocity. The derivative of velocity is acceleration, and so on. Good?
Yes.
So this is we get a rate that the arrow, the velocity arrow is showing to whatever this number meters per minute. So here, notice we actually solved for what was r as a function of t. It is not generally convenient to carry out those calculations, as they can be very, very difficult. So here is, again, using implicit differentiation, we try to bypass solving for an explicit function of t. So we know this relationship. We know that a of t equal to pi rt squared. We related a and r. Now, it's uncomfortable to keep writing t's all the time. So I suppress t to make it more visually pleasing. I write a equal to pi r squared. Yes?
Yes.
But what you should remember, there is no a. There is really some formula that only involves t, only involves time. And that formula you already solved for this case. That would have been 2t in our example, right? And there is no r. There is no r. There is instead some formula, and that is this formula that only involves t. This is just an abbreviation because I haven't bothered solving in terms of t. I have those symbols, but really I see some unknown function equal to pi times some other unknown function squared, and all of them are functions of time. Yes, and we will use chain rule. So guys, if you are don't feel pressed. If you are confused by something, please always stop me, right? And we can talk it over. Yeah, so good. So we understand it, right? And then I take the derivative by implicit differentiation. I take the derivative of the left-hand side in terms of t. Guys, that surprises me. I post those videos on my website. So I post my notes on the website. So everything that I go over that's why I spend so much time. I write it in hopes that what I write can be read in case you don't want to watch a video, that you can do it. Okay, so make sure that you look through my notes and read them. So the a dt, I take the derivative of a with respect to time, equals to the derivative of the other side with respect to time. And that would be pi times 2 times r times dr dt. I don't, you see, because again, I'm taking derivatives of two different functions, but all of them are functions of time. I take it with respect to t. Good. So what do I get from there? From there, I have this equation. So dA dt is always equal to 2 because the speed with which a is changing is always 2. It's given as 2. Now the speed with which r is changing varies. So I have this equation 2 equal to 2 pi r dr dt. Thereupon I divide by 2 pi r and I obtain that dr dt is 1 over pi r, right? And then I can solve the following. When t is equal to 6, a is equal to 12, and r is equal to root of 12 over pi. Because as soon as I know a, I know I need to divide it by pi to get r squared and then take the square root. And so the r dt is given by this number, which will turn out to be identical to the number obtained right above. Okay? So that's how they work conceptually. Every other problem, be it difficult or not, all you have to understand is that there are two quantities, each of them functions of time, that are connected by some equation. Okay, so where are we now? So here is another question. Air is being pumped into a spherical balloon so that its volume is increasing at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when diameter is 50 centimeters? So before you solve this question, tell me what is it that you imagine, the bare bones. You should imagine a YouTube video. What do you see in this YouTube video?
Well, if air is being, are we considering that it's a two-dimensional or is it three-dimensional?
Well, we speak of a sphere. So a sphere is three-dimensional.
Three-dimensional, so okay.
Balloon, pump, and time bar.
Yes, but balloon is very vague, right? What is, when I ask what do you see, you have to see a YouTube video and you have to see it through the eyes of mathematics or through
You
the
want
eyes
us to
of
visualize it.
Yes, but visualize not even, you might imagine balloons, but I wonder what sort of balloons do you see in your mind. I see something much simpler, you understand? I see in this case, and I'll show you what I see in a moment. I just want to know what you see.
I imagine something expanding, a sphere expanding.
A sphere expanding, brilliant. And so what you should imagine is you have a small sphere, then you have a bigger sphere, then you have a bigger sphere. You have something rather simplistic, yes? So this is what you should see. So if you play this video, you will see a sphere. Doesn't matter, it's a balloon. It has really no relationship to a real balloon. Real balloons are way more complicated, right? So it's just a sphere that's growing. What can you say about its growth? Well, it gets its volume is growing at a constant rate because volume is proportional to the air you pump in, apparently, right? So the balloon will grow at a rate of what was the rate? It will grow at the rate of 100 cubic centimeters per second.
All right. Can we try to figure it out?
Yes.
Can we do it on our own? Okay.
Yeah, go ahead. But you need the formula for the sphere, which is the relationship between the radius and the volume is that volume equals
4 over 3 pi r
4 over 3
pi
pi r cubed. So
yeah.
V equals to 4 over 3 pi r cubed. And Alexa, right, so you're asking questions in physics. I will show at least below a little bit about physics if we have enough time or interest. So in the notes, I mentioned how those ideas, when they are trying to be more realistic, how it becomes closer to physics. Of course, by then it becomes very, very complicated problem.
What is the formula for volume again? 3 over 4?
Yeah, I'll write it over here. You sound very sad, but don't be sad. So it's pi r cubed, and then we have here 4 over 3.
Thank you.
Jeff Suzuki, by the way, has pretty nice videos even about trigonometry. I will send you some of them. There's something interesting about him. His book many years ago was the first math book that I've ever gotten. And it was not even in here, it was just complete by accident that he ended up also being a professor at this university.
Professor, can you scroll down a little bit so I can see the picture you draw, please?
Sure.
Professor.
Add me on Steam. You want to cook me or something? I don't worry, guys. I am in hell already.
Professor, I have a question. Yes. For the volume for dv d over t, can we just consider that 100?
Yes, because volume is changing at a constant rate.
So 100 is equal to 4 pi r cubed. Pi r squared or pi r cubed?
Well, it cannot be squared. You can remember the number on the top of r has to do with dimension. So you relate a one-dimensional quantity to a three-dimensional quantity, it would have to be r cubed.
Right, but when you take the derivative, it's going to be 4 pi r cubed.
Yes,
oh,
r squared.
4 pi r squared.
Yes. Yes.
How does that work? I'm trying to think of it like mathematically and visualizing it. Like,
well, you solve as much as you can. I will explain it.
Okay.
So we are looking for the volume?
No, I mean, you're not looking for the volume. What are you looking for? You want to predict how fast is the radius expanding when radius, you see, when you press pause, I even drew it over here. When you press pause, radius happened to be 25 because diameter was 50. I made it simpler, right? Diameter 50 means at the moment when you paused, radius was 25 centimeters. How fast is the radius growing? You're trying to figure out the speedometer. What is the speedometer on the radius showing?
This is physics, no?
It's much easier than physics.
Oh my God.
I will show you physics below.
Okay, give me a second. You said something about chain rule before?
It doesn't matter what I said. You said try to figure it out if that's what you want to do, and then we will talk over it.
Yeah.
Am I supposedly on some Steam, by the way, Abdul? I'm not sure what you were asking. Yeah, I know, but why am I there?
Is it 1 over, hold on.
More important are formulas than numbers.
Can we just leave it in like a formula format?
Well, that depends. You see, I want to be sure that you know how to figure out. We're interested in the speedometer, not the speedometer of r, not at any moment, but specifically at some moment of time. Doesn't matter which it is, right? Where it's equal to 25, where r is equal to 25. Okay.
So, So for what I got is that dr d of t is equal to 25 over pi r squared.
So 25 over, it's numbers. Okay, 25 over pi r squared.
So now
Something.
since r is equal to 25, then
there is something else. Okay, so I think if there is a mistake, your mistake is not major. Let's see this together, guys. So first of all, volume, as we mentioned, is 4 over 3 pi r cubed. When I see this, I imagine that, well, volume is some function of time. In this case, I could even predict what it might be. It might be something like 100t, but doesn't matter, right? It just, in general, it's some complicated formula of time. And r is possibly also a complicated formula of time. I see something in time equal to something else in time. So when I take the derivative with respect to t, dv dt is the best I can do when I differentiate symbolically. That's equal to 4 pi r squared. So here I use chain rule, right? So I have a function of t cubed. So using chain rule, what happens is that the 3 drops down, cancels this 3 below the 4, and I get 4 pi r squared, and then the derivative of the inner function, which is dr dt, right?
yeah.
So dr dt, which is 100, equal to 4 pi r squared dr dt. Which means when I divide, right,
Right.
by 4 pi r squared, look at it, what happens here, right? So 100. So here, right? So we have 25 over pi r squared, correct?
That's what I got.
That's what you got. Brilliant, right? So 25 or divided by pi r squared. That's my dr dt for all time. Notice it's in terms of the radius, yes? And then I put in r equal to 25. When r is equal to 25, I can cross out one of the instances of 25, and I get simply 1 over pi times 25. That's my rate of change, and I can simplify this number or approximate it. It will be 1 over pi times 25 centimeters per second.
Yeah, I was heading there, but I just didn't know exactly what to do at that last part. I was saying since r equals 25, and then I got lost after that.
Right, so you have to then interpret, which means that when, I'm not sure what time this happens, but at the moment when radius happens to be 25, the speed of change is 1 over pi times 25 centimeters divided by second, okay? Are you with me, guys? I hope you're not, don't feel diffident. It's a very difficult topic when you learn it for the first time. In some sense, it's not useful to spend 1 hour or one lesson on it. You probably have to spend 7. Okay, all I can do is, well, this is not really a physics example. All you can do is slowly just get the idea of how you think about those problems, and then eventually it will be, it's stereotypical. Here is another example. Okay, guys, so get ready, and we will solve it together. Ladder is 10 feet long, and it rests against a vertical wall. The bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? You understand what's the question? So before you even get to the nitty-gritty details, what am I seeing? If I play this on a YouTube video, what am I seeing? And of course, you might speak about ladders, but that's not essentially what I'm seeing. What truly am I seeing for the problem?
Can you see my screen?
No, because I'm not allowing share screen for my students.
No, can you see me? Can you see me?
Okay, let's see.
Wouldn't the what is it called?
Yeah, I can see you.
You're looking at the ladder that's tilted on a wall. This is the wall. The ladder would fall.
Yes.
Like this.
Yes.
That's what we're looking at.
But I want you to describe what we're seeing, the gist of it, because obviously that's not about ladders, right? What is from a mathematician's eyesight? What is it that you are seeing?
The slope is are we considering that or no?
Well, you see, No, you see, when I here's
triangle.
Exactly. Now that's brilliant. A triangle. Okay.
Mm.
When you start speaking about slopes, you're being a bit. You see, it's like with a bad, unskilled camera recorder. You're giving me a picture of a donkey, right? And you're showing me a donkey's tail or a donkey's ass, right? That's not. What I asked you, what are you seeing? What is it the video of? And that video is of a donkey. Yes. So in this case, it's a video of what?
A ladder.
No.
A triangle.
You got me, Darnell. You got me.
A
Right?
triangle. You said it before. You said it before.
What
Triangle.
I was saying is that
Triangle. Yes.
you would see the angle of the ladder where it meets the floor getting smaller and smaller.
Yes, all of it is wonderful. All of it is good. But triangle is what's the type of triangle? Right triangle, because the wall, if it's a good, well-constructed house, the wall is perpendicular to the floor, and the ladder is always in contact with the wall and the floor, making a right triangle, right? So the fact that I say it's a ladder, it's way too simplistic for a real ladder. If you open the physics book that I mentioned, there is an example of a falling ladder, and it's many levels more complicated than this problem. Okay, so here what you're truly seeing is a bunch of right triangles, right? And you can see as the triangle slides from the wall, you can see that as I think Darnell mentioned, or maybe as Joel mentioned, is that what you're seeing is the slope is getting less steep. It's getting closer.
Realistically, you would have 3 triangles then if you're taking all counts into.
Why 3? You have infinitely many. You play a video, so you have. What do you see? You see this, right?
Yeah, but as the ladder is falling, you have other triangles that come in. I'm drawing it out right now as we speak.
Yeah, so you understand it's a bunch of right triangles that we're associating. Yes, that's beautiful. Yes, so what you drew is correct. Yes. So now, but what you imagine is truly not a drawing. You imagine an animation. It's just rather costly to produce an animation. But
Sure.
in your head, you should play primitive cartoon. So tell me, please, then, what is going to be the velocity of the top of the ladder when the ladder is 6 feet away from the wall at that instant?
Can you say it again? I'm sorry.
Well, you can see the question. Yes, can you read it? So
yeah, okay.
I'm gonna try to solve this question.
You have a bird, Professor?
A bird? Well, something of the sort, yes.
A parrot?
That's good. I have plenty of parrots.
I love parrots. I used to have one also.
Which parrot? Kakadu?
No, I had a yellow-naped Amazon. She's at my uncle's house now.
Oh. How old is she?
She's probably around 4 years old, 5 years old now. Maybe a little older. We got her when she was a baby.
Professor,
Yes.
so if it's a right triangle,
Mm-hmm.
so we can say that because it's 10 feet the ladder, so it's basically 10 square, right? Because if it's a right triangle.
You're probably thinking of what? Of Pythagorean theorem. So
yes.
when you say 10 squared, you probably mean you want to relate it to these
right.
sides.
So if you have one side plus the other side equal to the third side square.
Yes,
can
each
I
of
use
them
that?
squared. Well, of course.
Okay.
Don't be not assured. You should know what you can or what you cannot use. It's like when you know a person. It feels almost the same way.
Okay, I'll do that and I'll be back.
Oh, so we're gonna do, in this case, so it would be x squared plus y squared is equal to 100.
Yes.
Okay. And that the derivative of x is going to be 1 foot per second. Precisely.
Yes. Always, right? So that's not how a physically falling ladder will behave. It will be much more complicated. But here the bottom of the ladder is always moving away from the wall at 1 foot per second. You're a lot more shy than my other class guys. I only see what 2 people here. What about the rest of you? You don't like me to watch you, to see you?
Anyway, you can see all of us at the same time.
I can see at least I can see at least 6.
Really? Let me see.
Actually, yes, 6. Well,
I see 2, and you.
Mm-hmm. I can understand that you're being watched anyhow by too many people.
Professor, 2x plus 2y is equal to 0 after you're taking the derivatives.
Be careful. 2x.
2x d derivative of x plus 2y times the derivative of y is equal to 0.
Now it's good. Now it's good.
I didn't understand how the derivative of x equal to 1.
Derivative of x with respect to what? X is
to
moving.
The time.
X is moving as a function of time.
Mm-hmm.
I will
so
explain
because
all
it's
of it.
1 foot per second
Right. So
okay.
it means that x is really changing in time. I will show you once we go over the problem. I will show how to solve it, right? And then
okay.
You were on the right path, Batel. You were doing it. You were saying that x squared. You were doing Pythagorean theorem.
Yes.
You were doing Pythagorean. So from there, you want to take the derivative.
Now I need to look for derivative of y with respect to t.
Exactly.
Okay.
Yes. Good. Professor.
Yes.
Hold on. So you paused the video at 6 feet.
Yes. So because you don't know when it was when you started recording, there is no any physical sense for asking what time it was paused, right? So you just move the cursor of time until you see that the ladder is fixed 6 feet away from the wall.
So x is realistic. So it's x is equal to 6.
Precisely, x is 6, but it's not equal to 6 in only when you press pause. Yes,
right.
Brilliant. Then you see the video very well, right? So just when you press pause for that moment, x is 6.
So then what you're gonna do after you subtract after you compute 2x, what I said before, remember equaling to 0, that whole mishkababu, that whole 2x times derivative of x over derivative of x plus 2y times the derivative of x over 2y times the derivative of y is equal to 0.
That's beautiful.
Hold on a second.
Professor, can I ask you a question?
Of course.
Okay, so after I found the derivative of y, I can plug in the 6 because you said the 6 is equal to basically x. So I can
Yes.
plug it into the formula and find the y.
Yes.
And then what?
And then you have everything ready. You're almost there, right? You have x, you have y, and you have dx, ddx, dx dt, and dy dt. So you need to figure out.
So I plug it in the dy dt.
Well, that's what we want to find out. We don't know what's dy dt, right?
Okay.
Professor, is it dy dt is equal to negative negative x over y?
Yes.
And that which negative x over y times times dt over dx over dt.
Yes.
Oh, I'm messing up here. Hold on.
That's good. All right. So whatever you got, it's already very good, guys. So you want me to wait? Okay, I'll wait.
Yeah. Wait. I'm almost done.
Okay.
Professor, but how are we supposed to
do what? To know it very fast?
Yeah, to come up with formulas on our own. It's every question can be a different formula, so we need to be brilliant.
No, I mean this is very far from brilliance. But it does take time, guys. It's not like in a second I figured out how to deal with it. I spent some time. I thought about it. Some questions can be very hard. Some are not as hard. But you realize once you are experienced enough, you start seeing that it's very stereotypical. So
but
many
you're not gonna give us the formulas.
Formulas. So most formulas, let's say formula for the sphere is something that you are not yet supposed to know. But other formulas, let's say the Pythagorean theorem, you're not only supposed to know, in my opinion, you're supposed to know how to prove it. I did it in office hours, and I might still write lecture 1 for trigonometry to complete it. And I will show you, I will send you videos by Jeff Suzuki, made videos on trigonometry as well. So,
Professor?
Yes.
So since we have a 10-foot ladder, and it's paused at 6, x is equal to 6, you're going to get y is equal to 10 squared minus 6 squared?
Precisely. Y squared is equal to 10 squared minus 6 squared. Y is equal to the square root of the number.
Yes, so y is equal to the square root of that. So that's going to be equal to 6. So that's going to be equal to square root of 64.
Yes.
So the answer is 8.
Precisely. Well, the answer on the numerator is 8. On the denominator is 6.
Right. So then.
Yes, you got it. You got it. That's beautiful. It's very good. Very good work. Just very good. So we will discuss it right away.
But you help us.
Yes. Well, I'm not sure how much I helped you, but hopefully you just. Here's what I do, guys. That's the only difference between what most students do and what I do is that I try to be friends with the formulas. In other words, I try to really get to know them. You know, what they are about, why they work, why they don't work, anything. And then it's easy to figure out many things.
Okay, let's see the way.
Okay, so here is the animation, right? So here is the ladder. When I move the time, the ladder slides down. In essence, from there, I'm not really even thinking about ladders. I'm just seeing a right triangle and I'm seeing another right triangle. Yes? Yes, so yeah, Alex, don't tempt me too much philosophically just yet, so I'm not distracted. Afterwards, I will speak about some interesting things. Yesterday, I had some interesting questions that I assigned for the exam for probability. So we have the relationship that by Pythagoras theorem, we know that since we are always seeing right triangles, here we see that both y changes and x changes. X will grow and y will diminish. But always we get x squared plus y squared equal to 10 squared. That's by Pythagoras theorem. So what do I see? I see x squared plus y squared is 10 squared. I forgot to put a square there.
Okay.
And when I take the derivative, you remember, what am I truly seeing? I'm seeing some function in terms of time that I did not bother to solve for. So I'm seeing this function is squared. So I'm seeing by chain rule 2 times x times dx dt plus 2 times y dy dt equal to the derivative of 10 squared, which is 0. Are you with me, guys? Right. So you see where I get, this is the most important part. Do you see where I get dx dt, dy dt?
Is it the derivative instead of writing x like with a prime on it?
Yeah, you can write it with a prime. Just remember that in this case we take the derivative not like in previous questions we had to find y as a function of x. Here both x and y are controlled by a third parameter, which is time. Right?
Okay.
So really, I don't see an x, I don't see a y. In my head, I imagine I'm like drunk and it's very hazy. And what I see is a formula of t squared plus another formula in terms of t squared. And because I'm so drunk and hazy, I do not see what the formula is really. So I write by chain rule, it's 2 times x times dx dt. That's chain rule plus 2y times dy dt. And that's equal to 0. Yes?
Professor, I think I simplified it down to -3/4.
Yeah, why not? That's good. And then what do you do, guys? And then you can solve, right? You can move things around. So I take this part, 2x dx dt, I move it across the equal sign, and I divide by 2y. You see, this is just now, I'm solving for this guy. So everything that's not involving dy dt, I move across the equal sign. I get minus 2x dx dt. And then I divide by 2y. And when I simplify, the 2's cross out, and I have minus x over y dx dt. Now dx dt is given to always equal to 1. In other words, x, this thing is growing always at a constant rate. It's like if this x, let's say what happens here is, imagine that a remote control car is dragging this ladder, and it's always dragging it at a constant rate. Make sense? So the speedometer on the car is always 1 foot per second. So dx dt, I can just replace it by 1. And I get that dy dt for any moment of time, it's minus x divided by y. That's for all time. Now, I am interested only at the moment where x happens to be equal to 6. So when I press pause here, I wait to press pause until x has grown to equal to 6. And if x is equal to 6, then y, by Pythagoras theorem, is 100 minus 6 squared, 100 minus 36, and I take the square root of that. So that's the square root.
Square root of 64.
Yeah, so by that's Pythagoras theorem, I have 10 squared minus 6 squared, that's the root of 64, which is 8. So at the moment when x is equal to 6, I have minus 6 over 8 feet per second, which is minus 3/4 feet per second. And what does it mean, guys? 100, that means that the minus here means that that the y length is diminishing. If it's plus, it's growing. If it's minus, that means that it's like it's going to closer to 0. It's diminishing. All right, so I hope that explained it enough. Here is another problem of the same sort. Okay, I will help you at least a little bit because I'm not sure you know the volume for a cone. So we have a tank, a water tank, and the tank is inverted circular cone with base radius 2 meters and height 4 meters. Okay, and then water is again pumped into the tank at a rate of 2 meters cubed per minute.
Isn't the volume of a cone like 1/3 pi r squared times height?
Yes.
It's geometry.
This is yes. It's but again, so I think one way to prove it is to use calculus, a technique that we will learn later.
Do we need to know these formulas?
I don't think you do. Right, for related rates, usually at this stage you are. I don't think you know how to derive this formula, how to verify that it's true. So I can easily derive that it's true using integration theory from calculus. So I do use calculus, but some ideas we haven't covered yet to figure out what's the volume. Okay, so it's 1/3 pi r squared h is the volume of a cone. See if you can solve this problem, or at least try to set it up, please.
So first thing we do is draw and
yes,
up all the
draw and
information
also
we know.
imagine in the simplest possible way, because when you speak about water, what do we know about water? It's complicated, right? Water is not really the essence of the problem. What's the essence of the problem from the point of view of mathematics and geometry? That's what you have to realize. You are playing a video of what truly?
Okay.
Are you doing this with us, or do you want us to solve it on our own?
Up to you. I mean, I'm happy to do it with you or to wait for you to solve it.
I'm willing to do it on my own, but it's up to everyone else. I don't care.
All right. So work on it. Maybe what 7 minutes. Let's do 5 minutes. Try to set it up, and then we will go on. Only the setup is essentially what I want. Right? Can you figure out how to set it up?
When finding the derivative, is h constant? Is it?
No, you have to decide what's important. You have to decide which quantities change with time. H, if you say H is how deep is the water.
Oh, okay.
So is it constant? And thank you, Sam, so much for sending me the information about the final.
In this case, we only care about the radius and the height and the volume. Yes, Professor?
The height and the volume, correct.
So therefore, we can just try to get rid of r, the radius?
Precisely.
Okay. So the radius is going to be 1/2 times the height. After realizing that the radius divided by the height
That's wonderful.
is equal to 1/2.
Yes.
But how did you get to it?
Yeah. So yeah, I will explain, guys. So let's begin, I suppose, guys. So better don't be so upset. It takes actually quite a long time to figure it out in real time. So 5 minutes is not necessarily a lot of time, especially when you just are introduced to the topic. So here is what I see. This is the animation I'm seeing, and water is not really an issue here. What I'm seeing is I see a big cone, the dimensions of the big cone is radius equal to 2 and height equals to 4. And inside of it, I see smaller proportional cones. It's symmetric. Proportional because you can see it's filling in the inside, right? So it's proportional cone. And its height at any moment of time t is some height h. That's the that's how deep this water is, and r. Okay, that's how wide is the puddle on the top. Okay, so what do I observe here? So what do I observe here? Mute me, guys, if I hear my own echo. Maybe I'm already having schizophrenia, but yeah. So what happens here? Look at it. So if it's proportional, what does it mean? It means that the ratio of 2 over 4, 2 divided by 4 is the same as r over h. Does it make sense, right? It's like the measurements have to be related to one another. So 2 divided by 4, which is 1/2, equals to r divided by h. That makes sense? It's like you know, how do you minimize it, right? If it's say my finger is as long as my nose, it means that the ratio of my finger to my nose is equal to 1. And if you made a small model of me, the finger might be much smaller, the nose would be much smaller, but it should still be true that the ratio of length of finger to the length of nose is 1. In this case, the ratio of the radius to the height has to equal to 1/2. So
Right.
r over h is 1/2. I really want to know the volume of the smaller cone. Yes, what do you want to say?
So when we want the, what is it called? So by doing the radius divided by the height, giving us 1/2, we're trying to get rid of the radius in the formula for the volume.
Absolutely. Right. So we have this formula for the volume. I don't need the radius because I'm asked how deep, how fast is the depth growing. So I'm not asked how wide it's becoming. I don't really want the radius here, right? I want only, I know the volume, how fast the volume is growing, and I want to know how fast the height is growing.
So what you're gonna
I want to get rid of this guy.
So what you're gonna write is you're gonna write for the volume instead of that formula over there. You're gonna write volume is equal to 1/3 times pi times 1/2 h squared
Precisely.
times
So,
h.
yes, times h. So you can see it over here. Yes, right, guys. You see it here. Volume is equal to 1/3 pi 1/2 h, because that's what r equals. R is r over h is 2/4, or r equals to 1/2 h. R equals to 1/2 h. So I have this formula, and this formula enjoys the lack of r. It just only relates v to h. Yes, but what do you want to say?
I hope it's not a stupid question. But
Don't worry about it. Relax.
I still didn't understand why r is 1/2 times h, because you said proportional.
Yes, but so we can talk about that. Does it make sense what's proportional? So if I have two objects, right? Two objects, they are not of the same size, but they are similar, right? So the idea of similarity, it's a pretty complicated similarity. How do you know if I made a statue of you that is smaller, right? Let's say a smaller statue, maybe it's twice as small. What happened is that every feature that you have is now half the feature you used to have, right? So let's say the finger will be half the length, the nose will be half the length, the width of the lips is half the length, right? So how do you express this idea of proportionality, right? So if I'm holding, let's say, this finger, I say, well, my finger and my nose, just for simplicity, let's say that the finger and the nose are of the same length, right? Or maybe, let's say, if you want other measurements, let's say if I measure my face with my finger, it will be 2 fingers equals the length of my face. I'm making a simple
okay,
right?
Thank you.
2 fingers, right? So it will be true even for the smaller object. If I made smaller, it will be still true. So that means that the ratio of the length of my face to my finger is 2. Right? So over here, I observe which are the properties that I want to know. Well, we have the radius 2 and the height. right? How do I know they're proportional? You can see they fit snugly, right? So that means that this angle is the same. That means that this right triangle is pretty much like the bigger right triangle. They look alike.
Yeah.
So I have 2 divided by 4 equals to r divided by h, which
And
means
the-
1/2 equals to, this is 1/2 equals to r divided by h. And if I
And the-
multiply by h, I get r equal to 1/2 times h. Yes, I'm sorry, what were you saying?
And the length on the top also will be half because it's proportional,
Exactly. Proportional throughout.
or no?
Throughout the whole cone, it is proportional throughout. Right, Professor? Is that true?
Well, one second. Just 1 second. I want to answer to this comment, and then I want. Sorry to interrupt. I will head out and review them. Okay, it's fine. All right, Ellie, no worries. Right. So review it later. So guys, okay. So what were you saying, Joel?
What Patel was saying. I'm trying to clarify what Patel was saying, that it's proportional throughout the whole cone, no matter where you are.
Yeah, if you take any 2 properties, if you measure within the small objects any 2 quantities, one against another, and you find the corresponding quantities in the bigger object, the ratios should be the same. You understand?
Okay, I got
That's
it.
the idea of
That's it.
proportionality. It's the idea that how do you know that the object is not distorted, right? So in this case, I'm caring about I want to get rid of the r. So what do I observe? I see that the radius of the big cone divided by the height of the big cone is 1/2, which
Okay.
means that for any other smaller cone that's proportional, the radius of that cone divided by the height will be always 1/2. Okay.
Thank you.
Okay, makes sense. So then I know that r over h is 1/2, which means r is 1/2 times h. And then I replace it into this formula, and I finally get that v volume is 1/12 pi h cubed.
Mm-hmm.
Okay, and then I begin taking derivatives. So the derivative with respect to time of v, it's dv dt, that will equal to 2, because it's constantly 2. The volume is increased by 2 cubic meters per minute, something like that, right? And on the other hand, if I take the derivative over here, 3 drops down, and I get 1/4 pi h squared dh dt. Right? Again, they're only functions of time, I see. So then I go ahead and I solve, right? What I will get is once I just move everything across, and remember that my height is given to me. I want to know when height is equal to 3. So instead of h here, you can now place 3. Right? I'm interested in the h dt when h equals to 3, so that would be 9. That's where I get the 9 over here. So I get 8 over 9 pi, and it's roughly 0.28 meters
Wait,
per
Professor.
minute.
Wait, Professor.
Yes.
Can you? I finished where volume is equal to 1/12 pi h cubed. That's where I got. That's
Okay,
where
that's only the volume. Yeah, and now
I
we
have
need
no idea what to do after that.
but that, okay, so that's only the setup. So now you relate volume to h. Now I want to know how fast is h changing. So I want to know the h dt. Correct? I want to get to the h dt. So if I take the derivative with respect to time, volume with respect to time is dv dt. This quantity with respect to time will be 1/4 pi h squared dh dt. So does it make sense?
Yes.
Yes.
Based on what we were talking about before.
Right. So again, guys, very important. You have to imagine it. It's very simple. I do not see a v. I do not see an h. I imagine some formula involving only t on the left and some formula involving on the t here instead of h.
Professor, can you repeat what you said before again about how we spoke about it before? You said that. I'm trying to explain. I can't even express it in words. That's how. Like we have to know something in order to find the derivative of v. I'm trying to explain it. Whatever. Just continue. I'm sorry.
No worries. So what I'm trying to do here again is relate the speed with which v is changing to the speed with which h is changing. That's why it's called related rate.
In order to do that, yeah. What do you do?
So I have now a relationship. I know that v equals to 1/12 pi h cubed. You yourself came with this formula.
Yes.
Yes. So then I take dv dt. Now dv dt, it's given by the problem. I know that volume is changing at a constant rate. The rate is 2. So dv dt equals to 2.
Got
yes? And if I take the derivative on the other side, again, I use formal differentiation. In other words, I differentiate to the best of my ability, but since I do not have a formula for h, when I differentiate h, I write dh dt. Or if you prefer, you can write h prime, as long as you're not confused.
I thought we're getting rid of the h by putting in a 2, but 3.
We're getting rid, yes, we're getting rid of this afterwards, right? So first I need to take the derivative, and I have this relationship. That's 2 equals to 1/4 pi h squared dh dt.
Okay.
Good?
Yeah.
Yes, and now I'm only interested in this problem not for any arbitrary h, but when at the very instant when h equals to 3. That's where I put h equal to 3 here. So then I solve, right? So what I get when I solve this expression, I get 8 divided by 9 pi meters per minute. So
can you explain what you did before that? You see over there
what I did, I just solved a very basic equation. I multiplied by 4 both sides, so 4 times 2 is 8, and then I divide 8. I wrote it clumsily by accident. Really, that's why I put a -1 afterwards, right? Really, what do? I take this thing and I put it at the denominator of 2. If you prefer, you first multiply by 4, so it's 8, and then I put pi h squared on the denominator of this number, right? So it will be 8 divided by 8 divided by pi times 9. Okay, so I basically I imagine just carrying this thing and putting it at the denominator of 2, and then simplifying. Okay, so this is just what you call algebra, right? So 8 over 9 pi is then my answer.
Awesome.
So here is another problem. Okay,
is
one
this
more.
One hard?
I don't know. I don't think any of them are that hard. They can be much worse.
I mean, this past one wasn't easy. I'm saying, will it be if this one wasn't?
They could be this question. So any question in mathematics can be made very difficult, right? So this could be a very difficult question, surely. Yes, it could be a question that will take me some time to figure out. It could be a question that I would not figure out. Why not? You can create very, very complicated questions. They are in general very complicated. So a man walks along a straight path at a speed of 4 feet per second. The Gesundheitsgestapo, if you know what that means, casts a searchlight located 20 feet from the path, and the path and it keeps this man in its focus in light. Okay, so here is the picture, very much relevant to our time. So this person is walking out of his house. We have to be sure that he is not, that he is basically saving people. So you can see that here is 20 feet away from the wall. That's where the searchlight is, and the searchlight has to follow the man as the man is walking. Does it make sense? So the question is, how fast must the searchlight be turning when the man is 15 feet away from the initial point, from this point?
It's going to be opposite over adjacent. You want to relate. You want to put x with theta.
Wonderful. So go ahead, write the formula, and we will talk about it.
It's going to be opposite over adjacent. It's going to be tangent theta.
Brilliant.
Tangent theta is equal to theta over x. No, tangent theta is equal to 20 over x.
Vice versa. Tangent is opposite. Opposite is x. X over 20.
My bad. You're right. X over 20. Tangent theta is equal to x over 20.
Brilliant. So the relationship between theta and x, the simplest relationship, I could have related x to this growing line, right? But this is changing. It's not nice, right? I prefer to relate x to 20. So x divided by 20 equals to tangent theta. Here is that picture. X over 20 is tangent theta.
Yep.
And then your goal is to figure out d theta dt, correct? When x is 15, giving this information. Go ahead and calculate.
This is very similar to kinematics.
It is kinematics.
Yeah, pretty much. I remember reading a lot about this a few years ago. What is it called? Kinematic, like figure, body, constraints, whatever. I forgot, like the whole. It's something like that. I don't recall.
Yeah, so you might be predicting what I will mention in a moment.
Okay. Do we need to get the derivative of tangent theta?
Yes, well, we need to get the derivative of theta with respect to time, and for that we probably have to take the derivative of tangent theta. David Stein, you are quiet for quite a while. I hope everything's good.
Yeah, I'm good. I'm trying to do this.
I got 1/5.
Okay.
That's all I'm up to right now. If I'm even right. Am I right for some?
Well, let's since our time is approaching the end, let's figure it out.
I did exactly right till there.
All right. So if you set up tangent theta equals to x over 20, that's, in my opinion, half the battle, at least, if not more. So then when you take the derivative, I remember there is no theta. There is something in terms of time, and there is something in terms of time instead of x. So the derivative of the left is secant squared theta d theta dt. And that's equal to 1/20 dx dt. Now, dx dt is the speed with which the person is walking. And since he's walking always at 4 feet per second,
Yes.
so it's 4, right? So it's 4/20 or 1/5. Now, so d theta dt equals to 1/5 multiplied by 1/secant squared. In other words, I want to divide the right side by secant squared to have d theta dt on the left by itself. Now,
okay, wait.
1/secant squared is the same as cosine squared. Yes. What
can you say? Wait, can you start that part over after we got 1/5?
Yes, this part. So 1/5. So again, I see a secant squared multiplying d theta dt. I want to carry it across the equal sign. So I divide both sides by secant squared, which is what I see here.
Yeah.
Right. So d theta dt equals to 1/5 times 1/secant squared, but 1/secant squared is just cosine squared.
Yeah.
So just to simplify, I mean, this 1/secant squared is cosine squared. Okay, so I have 1/5 cosine squared. Now, what is cosine squared? Look at it. I want to know when x equals to 15, right? So I pause when x is 15. So this side is 15, and this is 20. So cosine squared will be 20 divided by r, right? And cosine squared, which I'm solving for, will be 20 squared divided by r squared. Now, r squared is 20 squared plus 15 squared. So it's 20 squared divided by 15 squared plus 20 squared, which when you simplify ends up being 16/25. So what I have now is 1/5 times 16/25, which ends up being 16/125. So the angle at that moment, the lantern is turning at a rate of 16/125 radians per second, or 0.128 radians a second, which means the turn is roughly 12% of a radius, almost 30%, 13% of a radius every second. Okay, so that is officially what we do for related rates. I would just like to briefly speak about how related rates are used in mechanics. Related rates, how are they used in mechanics? So here is a typical example. So imagine that in this picture you have a block, a wedge, sorry, and a block on top of the wedge, and there is no friction on the x-axis, let's say. So when you let the mass go, the object will begin, so mass will start sliding down and push on the wedge to move to the left, right? So it will make the wedge move to the left. If I play this animation. So the question is, how do you set up the constraint? So you have a bunch of things that are changing here. You see the horizontal position of the block, the vertical position of the block, the position of the wedge will change, right? Which I call as capital X here, right? So all sorts of things change here. And then one of the constraints in kinematics that you would have to figure out, for example, you can notice that if this block has angle theta, has height capital H, and so we see that at this moment, the position of the block can be described as follows. So the little h divided by this distance will equal to tangent of theta. So I have that capital H minus y over x minus capital X equals to tangent theta, which afterwards you simply differentiate with respect to time. Two dots means derivative with respect to time. Well, the acceleration, you need to take two derivatives with respect to time. So this is just typically what happens. So in almost every problem in mechanics and physics, you would have to have a related rates interpretation together with Newton's laws that you combine to solve the problem, to figure out the forces, to figure out everything else. And another thing is, again, guys, in terms of mathematics, a lot of people, if not out loud, they always say, but this is very hard. So no, what we are doing is not hard at all compared to how you need to know to even solve basic questions that are of interest. So for example, here is a question that I solved many years ago. I was rather happy. I knew very little to know physics, but I figured out how to solve it entirely because I had some training in mathematics. So this is a spring, and what you have to figure out is the spring is pulled to some position x0 and then released, and you can see this. The spring will begin moving the object up and down, back and forth. The question is, how do you predict what's the exact position of the spring at time t? We can go over that if you're interested, but the ideas involved, you would set up an equation. The equation relates to figuring out what function has a second derivative plus k divided by m times the function equal to 0. And when you go through the calculations, what ideas do you go through? You go through ideas of factoring a quadratic. You have, if you like, the number I is root of -1. You have relationship between the exponential e and trigonometry, right? With trigonometry, and once you go over all of it, you get this formula. You understand? So how many ideas did I go through to? That's not the way I solved it originally, but how many ideas did I go through to figure it out? I had to know deeply something about derivatives. I had to figure out that solving differential equations can amount to solving a quadratic equation or solving a polynomial equation where you have something squared plus a number equal to 0. I had to go through other ideas where I have to know that what it means to take e to the power of I, and so many other things relating e to the trigonometric functions. Right, and that's not the. Again, guys, I'm explaining it rather hand wave. I'm not explaining, to be precise. I'm just trying to get you to think about a level higher than where you are, to understand that it's not where you sit, it's where you hopefully want to be, if you want to be there, of course, right?
I think it's more like 10 levels.
No, I which is, again, right, I have a girl that, well, she took my Calc 2. Afterwards, I haven't seen her over the summer. Then she took my probability course, and then she took many other things. Right now, she's almost finished with the math major. I help her with graduate level complex analysis. She is ready to start the PhD program if she wants to. You can get to another level rather fast if you are interested.
Should I minor in physics?
I don't know. I mean,
Because this is interesting to me.
if it's interesting, I mean, minoring or majoring, it's I'm not sure if you need the paper or not. It's a bit stressful when you have to, or not interesting when you have to do what others tell you to, at least not to me, right? But I can recommend books that are interesting. I can recommend many things that are interesting. For example, here is a question I asked to my probability students, right? Related to what's happening now. Let me just tell you the question, you would understand it. So let's say that 3 million people are sick with a virus that they're very afraid of. And there is the test to go to check whether you are sick or not, right? The people go in line for it. The test is 99% effective. Let's say, that's by the way an underestimation, but let's say there are 300 million people in the United States. 3 million are assumed to be sick with the virus, and 300 million people that's the total population. Okay, so the question I asked is this: what's a better test? What's a better strategy, to go get tested or to flip a coin? You understand the test is 99% effective at detecting the disease if it's present. It's reliable 99% of the time. It's probably more reliable. My test is more reliable than the actual test. So the question is, what's a better strategy? Go get tested if you're worried, if you're sick, or just flip a coin?
Tested, but I'm sure it will be the opposite.
Well, don't be sure. I mean, don't try to predict what. But so
tested.
Okay. So it tested. What would do? If you get tested, what do you think? Say the test is positive. 99% accurate, test is positive. How afraid should you be? How likely is it that you have the virus?
99.9%, most likely.
No. That's the funny thing. No, right? The test reliably predicts if the virus is present. In other words, it's 99% reliable, right? So you think 99% that you have the disease, and you're wrong. That's the interesting part about it, right? So the test is supposed to be very reliable, 99% accurate. But let me tell you, if the test is positive, the probability you have the disease is 50%.
What?
Yes.
Professor, I actually have to go now.
Yeah, goodbye. You don't have to stay, guys. The lesson is over. Truly spend time studying this for this class, or otherwise it's yes. I can only accomplish how to study. It's very easy how to study. You have a book, you solve many problems, you read it. You can watch my lecture notes. There is not.
No, I was talking about the question before.
Ah, okay.
Yeah, I also want to know how from 99, 50%.
I will not. It will be a bit difficult to explain since you don't know the theory, right? But I can do it. But
before I go, I just want to say one thing. I just want to say one thing for the classmates. If you really want to get this in your head, I really recommend watching his YouTube videos as well, from what's posted on his website. Because honestly, those videos are so helpful. I understand it like this after watching the whole hour or 2 hour lesson.
Thank you.
And then in class also, obviously, both of them work. So
thank you, Joel. Guys,
I have to go. Bye, guys.
Take care, Joel. Another thing, guys, you see, it doesn't have to be even my lectures. There are so many. For Calc 1, there are millions of lectures available, right? The information is pretty much in your hands. I can help you only those meetings are way too short. You have to study, and you have to if you care about it, you have to study. MIT, if you can do whatever you like, but if you can read the notes, you can watch my videos if you want my take on the subject. Much of what I say is in consensus with what other people say. Hopefully, maybe I can give you some sort of view over the horizon. That's my view, not somebody else's.
All right, thank you, Professor.
Sure.
Have a nice day.
Have a good one. But 50%, guys, is then your probability of being sick if the virus, if you're tested positive. You can check the exam for probability is posted, and the notes are posted, right? You can check the questions, see if you're interested. There are many. I really love questions involving the exponential. All right. So if you have any questions, I mean, I will stop recording the video since the lesson is over. If you have any questions, you can continue asking those questions.